All right, guys, we're going to cover capacitors today. Capacitors are a circuit element that stores charge. Okay. So I have this warm-up planned. Typically in class we would do this, but consider two parallel conducting plates. So you've got conducting plates, and they're separated by an air gap or a vacuum gap. So there is no complete circuit here. There's no reason for the charges to jump across and close the circuit. But what I want you to imagine is that you have this bag of positive charges right here. So a whole bunch of positive charges. Of course, they're not happy about being together. All those positive charges are repelling each other. So if I have a wire connected to the first conducting plate, a lot of these positive charges are going to want to spread out. They're going to spread out as far as possible by accumulating on the first plate. Okay, so we've got positive charges accumulating here on the first plate. But on the other side, we have the second conducting plate connected to ground. So this is some rod connected to the earth. And remember that the earth or ground is an infinite source of whatever charge you want, right? The earth is very large. It has a lot of neutral atoms, and we can borrow charges, whether it be positive or negative. We can borrow as many charges as we want from the earth. So if we now have a bunch of positive charges accumulating on the left plate, then due to the attraction to those positive charges, we're going to start pulling negatives out of the earth, and they're going to start through the attraction to the positive charges, they're going to start accumulating over here on the right plate. Okay, so what we have now is a voltage across these parallel plates because of the attraction between the positives and the negatives, and we have something that looks similar to a battery, an accumulation of positive charges on one side and an accumulation of negative charges on the other side. And this is what we call a capacitor. This is storing charges on parallel plates. Okay, so what I'd like to do is look at how we can increase the capacitance. How can we make a capacitor better at storing charge? So if you look at the equation for capacitance, I always start here. That charge on a capacitor, so the total charge on a capacitor is equal to the capacitance, and capacitance is your ability to store charge. Okay, and the reason I always start with this equation, Q is equal to CV, there's a nice little mnemonic here, and that is CV, we're charged up. And I remember Mr. Zier, the physics teacher before me, he always used that, and it's pretty easy to remember there. That CV, we're charged up. So capacitance times the voltage on the plate is equal to the total amount of charge that you're going to be storing on that capacitor. Okay, again, Q is the total charge, V is the potential difference or the voltage across the plates, and C is, well, how well can these plates hold charge? How good are they at storing charge? So let's look at that next, the capacitance of parallel plates. If you think about those parallel plates from the warm-up, we have a positive bag of charges here. The other plate is connected to ground. Okay, well, what could you do to improve how many charges I can store on this capacitor, right? There's obviously a limit. There's a limit to how many positives are going to want to come out of this bag and accumulate on the left plate. Because eventually there's going to be so many charges on here that no more charges are going to want to come out of the bag and store on the plate because they're all repelling each other. So there is a limit. So you think about, how could I get more charges on here? How could I increase the attraction between the positive and negative side? Well, one way to increase the attraction would be to move them closer, right? The closer the plates, the more charge I can store because the attraction is going to be stronger. Okay? Another thing that we could do is we could increase the size of the plates. If we increase the size of the plates, then that allows for more room for charges to accumulate. Okay? So by increasing the area of the plates or by decreasing the distance between them, we could improve the capacitance. We could allow these parallel plates to store more charges. And the last thing that we can do is a little bit different. Imagine that we took an insulating material, okay, and we shove an insulating material in between the plates. And you say, well, insulators usually aren't used in electricity because they don't conduct current. So this insulator is not going to allow positive charges to jump across and neutralize with a negative charge. But what an insulator can do, even though charges aren't allowed to flow freely, remember that an insulator can polarize. The molecules themselves can reorient themselves. They can turn so that all the molecules line up. So that while I have neutral molecules inside of the insulator, they're going to turn themselves so that the negative side is on the left, the positive side is on the right, and all these molecules inside of the insulator are going to turn in this orientation. And what that does is it actually strengthens the electric field that we have in between the two plates. We have this uniform electric field, and the fact that each of these molecules are polarizing, they're increasing slightly the attraction between the left side and the right side because of the way that they've oriented themselves. What we call this inside is a dielectric material. It is an insulating material that we've put inside of the capacitor to increase the electric field, to strengthen the electric field and make our capacitance a little bit higher. So if we look at the equation for capacitance, we have a couple of things. We have area, that's what we predicted. If you make the plates bigger, you can store more charge. Distance, notice that it's in the denominator. That's because if you increase the distance, you're going to weaken the capacitance. If you pull the plates apart, they're not going to be able to store as much charge. And then this guy right here, epsilon naught, is what we call the permittivity of free space. This is how well does vacuum hold an electric field. How well does vacuum hold an electric field? And then we said one more thing that we could do to make this capacitor a little bit better was to put in an insulating material. So if we put in an insulating material, we're able to strengthen that electric field a little bit. So we call this guy kappa. Kappa, the Greek letter kappa, is the dielectric constant. Okay? If we put in an insulating material between the plates, we can actually get a better electric field than we could with just vacuum. So here we have kappa times the permittivity of free space. How well does vacuum hold electric fields? Times the area of the plates. We're going to do, for the most part, if they are parallel plates, we're going to assume that the area of each plate is the same. And when we calculate area here, you're just doing the area of one plate. So kappa times epsilon naught times the area of one plate divided by the separation distance between the plates. And that's the capacitance for this particular capacitor. We would have done a lab in the classroom, or we would use a textbook to find the dielectric constant of paper. So you can imagine doing this where we take a textbook, take two sheets of aluminum foil, and we shove them into the pages somewhere, okay? And then we hook up a voltage source to the aluminum foil, and we store charges on the aluminum foil, and then you would graphically determine kappa, or the dielectric constant of textbook paper. So I think there are sources there online. There might be some examples of that lab that you can find online. I'll start searching for maybe a simulated lab that you guys could do. But as of right now, just keep in mind that that's one of the labs that we would have done, and it's one of the labs that could show up as a free response question. That is, rearranging this equation or graphing this equation so that kappa would be the slope. So you could imagine graphing, for example, capacitance on the y and epsilon naught A over D on the x-axis. So that kappa would be your slope. Okay. All right, guys, that's it for now.